Hello. Okay. Sekejap remove. Yes. Boleh capture. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Sekejap Aku maximizekan screen. Okay. Semua nampak Sekejap sudah live. Okay, so can you guys hear me? If you can hear me, please say something in the chat box. Welcome to my live stream, guys. I hope everyone is okay. Tengah hari kan, ngantuk-ngantuk sikit. Okay, cepat-cepat join. Okay, so siapa join boleh letak dalam apa nama dia, chat box. Aku tunggu korang. Say something. Boleh dengar tak? Hello. Okay. Nampak tak? Hello guys, nampak tak? Guys, nampak tak? Dengar. Okay, hi Anas. Okay, welcome to the stream. So, kita start dengan direct current. So, this is the node. And then, kita pergi DC motors, which is direct current motors. I already given both of the nodes in the group. So, I hope you all can follow together. Okay, so let's start with DC. So direct current, why does it look like that on my screen? Sekejap kenapa dia macam ni? Nampak tak nampak? Sekejap, kenapa dia pecah-pecah Okay, ni okay. Kenapa di sini? Asal apa yang petak-petak tu? Sekejap Okay. Dah okay balik. So this direct current is a unidirectional current, and the flow of charge is always in the same direction, in one direction. So in our syllabus we talk about circuit analysis. So in a circuit there could be many components. There is a resistor, a capacitor, an inductor, voltage source, and current source. For a direct current, for DC, there's only a resistor, voltage source, and current source. So there can be a lot of arrangement of the components. So we talk about what is a node. Node is a junction of connecting wires. Every point on a node has the same potential. In the node, there will be always the same potential. So usually we will choose a reference node to keep track of all the different potentials in a circuit, which is this one. This is usually called a reference node. A branch is anything between the nodes. So this is a branch, this is a branch, this is a branch. A loop is a closed path that begins and ends at the same node. So, oh my god. Okay. So this square is a loop. This square big rectangle is a loop. So that is a loop. So now we talk about series and parallel circuits. So in a series circuit, there's only one path for current. The current is the same everywhere. Parallel circuits, all the resistors share a common voltage and the current depends on the resistance. Okay, so this is how a series circuit looks and a parallel circuit looks like. Okay, so this is the equation that you will get. This is the V equivalent, R equivalent, and the R equivalent for the parallel. So there are two types of analysis. Not two types. This is one of the first analysis. This is one of like a technique to solve a circuit analysis, which is a voltage divider. There is also a current divider. So we go to voltage divider first. Voltage divider creates a voltage fraction from the source. It is used to reduce the voltage from a big voltage to a small voltage. In other words, it is used to manipulate voltage. So imagine you have a series current, and then you want to find how much potential, how much voltage goes through the second resistor. So you use this. You use voltage divider. This is the equation, voltage fraction. So for current divider, is to create a current fraction from source. So a voltage divider divides voltage, and a current divider divides current. So that makes sense, right? So this is the equation for the current fraction. As you can see, usually the voltage divider uses a series circuit, originates from a series circuit. A current divider originates from a parallel circuit. So the equations are about the same. R equivalent equals to R1 plus R2. R equivalent equals to 1 over R plus 1 over R plus 1 over R. So that's the similarities between the voltage divider and the series equation, and the current divider and the parallel equation here. So now we talk about nodal analysis. So a nodal analysis is a process that uses KCL to determine node voltages. So we assume that the voltage, the potential at the reference node is 0. This one. This is called a reference node. So we write a KCL equation for each node. I equals to Vx minus Vy over R. So this is the R, this is the Vx, and this is the Vy. So yeah, this is to find the internal current inside this loop. There will be a lot of loops. So this is the nodal analysis. The loop analysis is a process that uses KVL to determine loop currents. So usually loop currents usually has like a voltage source more than one voltage source. If nodal analysis, there's more than one like nodes. Okay, so this is where there are a lot of nodes. This is where there are a lot of voltage sources. So okay, let me write there. Usually a lot of nodes. You use loop analysis to when the circuit usually have a lot of voltage, a lot of power sources lah. Okay, then we go to Kirchhoff's law. So there are two Kirchhoff laws. The one I mentioned, the one that we usually use for nodal analysis, KCL, Kirchhoff's current law, and Kirchhoff voltage law. Kirchhoff current law states that all currents entering a node equals to all currents exiting the node. Okay, this is like an equilibrium. What goes in must comes out. Okay, voltage law states that the voltage drop must equal to the voltage rise. So usually a power source is a voltage rise, and the resistance is a voltage drop, as seen in this picture. Okay, now we go to like a delta Y transformation. Delta Y, we call this delta because it looks like a triangle. This triangle here. And then Y is because it looks like a Y. That's basically it. So you can transform one network to another network by using these equations. Okay. This is a Wheatstone bridge. You use this is to balance two legs of bridges, a bridge circuit, which means that the circuit going here and circuit going here is equal. So in between here there is no potential difference. Okay, that's it. So that is direct current. It's not actually cover a lot, but it's just like an introduction to direct current. Okay, so now we move to DC motors. So DC motors is a quite complex topic lah, but we go this together. Okay, so first we talk about power. Power is a main component in motors because that is what makes it turn. So power is work over time. Work is force times distance. Usually you use force to move an object about a distance, and that distance times with the force over the time taken is what you call power. Okay, so in the motor, this is what we call a linear system. And then we will talk about this is a rotational system. So for a rotational system, you have force, you have this, you have a circle, you moving in a you are rotating, and the distance is denoted as r times theta. Make sure you guys use radian. Okay, so force times r theta over time, because the distance is r theta, so we can say as force times r theta over time equals to the power. So what does this got to do with motor? It is because the equation for a power for a motor is torque times angular velocity. Okay, torque is force times r, angular velocity is theta over time. So you will get this equation. This is what we call the mechanical power of a motor. The power equals to, is in watt, torque times angular velocity. The torque is Newton meter. The angular velocity is radian per second. This is quite different from our lecture note, because I think our lecture note uses a very old textbook. Dia punya angular velocity is denoted as n. So it is not actually very dia macam memeningkan lah, because n has a lot of meaning. You can have like number of turns. This is a problem I face while reading the lecture notes. So why don't we denote it as omega, like we usually use for dynamics and other subjects. So this is the power of a motor. Power equals to torque times omega, which is the angular velocity. Okay, so now when we talk about the motor, there are a lot of things that correlate to each other. Okay, for example, torque is directly proportional to the ampere, what is called, the current. Yes, so usually you don't know what is the relationship or what is the exact equation for the torque and the current relationship. So what you do is you put a constant, like that, like force. Usually if you use force equals to kx. This is the spring constant. Okay, this is usually found in physics lah. So if you the relationship between torque and current is a constant, which is denoted as kt. Kt is the torque constant. This kt also comes in this kt is denoted as torque over current. We need to memorize the units, because usually they give you the units in Newton meter over ampere. Or there is another way to denote the torque constant, is to have a phi or a Weber. This is the like the unit for flux density. So kt prime is usually a torque constant per flux density. Okay. Per flux density. And then you kali lah dengan flux dia, which is denoted as phi. Okay, so this is torque constant. Kt equals to torque over I. And then we talk about back EMF constant. The EMF is directly proportional to the angular velocity. So the more you spin, the more EMF you produce. So just like just now, we put a constant. Oh my god. We put a constant to make a relationship between the EMF and the angular velocity. So it's denoted as E equals to EMF constant times angular velocity. So this is KE equals to E over omega. So this E is in volts. Don't worry. The simple way to memorize this is that both of the parameters are curly. You know, like one is like that and one is like that. So it's like a straight W, something like that lah. Faham tak? Dia macam W. Dia macam bengkok-bengkok sikit. Macam tu lah. Okay, so KE equals to E over omega, which is the units is V over radian per second. So that is the unit. So this EMF constant also can be denoted as KE prime. KE prime is also like the constant per unit flux, macam atas ni, per flux density. So the unit will have Weber over Weber. So usually the difference you can find is when they give you a value, let's say 30 V over radian per second times Weber. This is usually the difference with how you want to differentiate or they will ask you the EMF constant per unit flux. That is K prime, KE prime. Okay. So over here we have a circuit. So this circuit is a PMDC. PM is a permanent magnet DC motor. Okay, permanent magnet. PM is permanent magnet. So this permanent magnet motor is located here, and in that motor has a internal resistance. Usually we put the resistor the resistor component outside, or like just an easy way to denote, to like just an easy way to see it in a circuit diagram. So it's just a normal circuit. It's just basically like that je, macam tu. But this resistance is special because it is actually a motor. So okay, so there is a voltage source, there is a current flow, there is the resistance, and there is a back EMF. Why is there a back EMF? Because it generates electromagnetic forces, so it will give a back EMF. So okay, so this is the equations that we use. The electrical power developed is equals to I times E. Okay, this is in the unit watts. The mechanical power is torque times angular velocity, like we discussed just now. This is the mechanical power. So this is the mechanical power over here. The input power is V dot I. Usually input power, they will usually mention in the question as the power source if they don't use voltage source. Tak buka kamera, tak apa. Okay, so this is a power loss due to resistance. If they mention the power loss in the motor, let's say they will talk about power loss in coils, or power loss in the windings. They will say that, and then they will give you a value 10 watts. So that is actually the I squared R from power loss. Okay, so there is this equation also. The mechanical power is the electrical power developed minus the mechanical losses due to friction. If there is any lah. If there isn't, you can cancel this out. So usually it's just this. Usually it's just that. Okay. Torque times angular velocity equals to E times I. So the efficiency is the mechanical power over the input power. So the mechanical power is torque times angular velocity over V times I. Okay. So far so good. Ada soalan? Do you guys have any question? You can say in the chat box. If you guys don't, we can proceed. Do you guys understand so far? Alright, thank you Putra. Looks like Putra understands. Okay, so over here we have terminal characteristics. Ni dah cover whole topic. Oh, belum, baru start direct current motor. But basically dia cover lah juga banyak topik ni. Nanti aku explain dia punya contoh-contoh dia. Tapi basically cover lah juga. Dia beza sikit dengan lecture note. Sebab lecture note kan, dia macam bapak bosan tu. Tak faham. Sebab dia punya di note pun like beza-beza, nampak ni. Dia punya equation dia pelik-pelik lah. Dia macam tak memberi semangat lah. Pening gila. Okay. Okay, so now we go to terminal characteristics. Terminal characteristics ni is like how you would rate a motor lah basically. This like kita kan belajar pump kan. Pump kan ada pump characteristics. Ni macam pump lah juga. Tapi kita panggil dia terminal characteristics. So terminal characteristics ada dia punya graph dia. Okay. So what does this graph say? This graph is a graph angular velocity over against torque. So how much how the motor can give how much torque at a certain RPM. Macam tu lah orang selalu cakap. Ni RPM. Torque ni Newton meter. So what we can observe here at high RPM the motor will give you a very low torque. At a low RPM it will give you a very high torque. Okay, let us write there. Low RPM, high torque. High RPM, low torque. Okay, so what happens when the graph hits the axis? So this here is when you have no load attached to the motor. No load attached to the motor. Kalau apa? No load attached to the motor. Kalau dalam pump tu dia macam no head lah, no head. Kalau kat sini dia namanya stall. It's called stall because there is the angular velocity equals to 0. Angular velocity equals to 0. Torque is max. Because torque is max because it's like you stop the motor from moving. Tmax when the motor stops from the heavy load. Macam tu lah, lebih kurang. The load is very heavy that the motor stops. That is what we call stall. Over here, no load. No load means the torque equals to 0. Because no load, there's no beban on the motor. Okay, so this happens at a constant V. Let's say the V is equals to 10 volts. If the potential difference or the voltage source is lower, it will shift downwards. This one, wait, different color lah. Okay, this one V equals to 8 volts. Macam tu. Atas ni contohnya V equals to 12 volts. Macam tu lah. That is what the graph says about lah. Okay, so that is the graph. So right here we have we have a derivation. So let's say we have an EMF equals to V minus IR. This V is the voltage source and IR is the is the current across the motor and the resistance of the motor. Okay. This is the V supplied. I is the current across. R is the R coil lah, R winding ke R motor ke, macam tu, R motor. So this is the equations we came out just now. Torque equals to torque constant times current. The EMF equals to the EMF constant times angular velocity. So we put both of these inside here. So we get 1, then we get this one also. Okay, so this equation here, and then you put we times the equation with the EMF constant, and you will get this equation. Okay, what is this equation? This is the function of this. This is the function of this straight line. Okay, see, the angular velocity equals to the voltage over Ke minus R over Kt Ke times torque. So this is like an fx, f function of x. Wait, f function of x, but this time it is the angular velocity with the function of torque. Sini angular velocity and torque. So it's a straight line. It's a straight line. Okay, because it's a negative R over. So this is the gradient here. Macam maths lah kan? Macam maths. Okay, so when torque equals to 0, V over Ke. So when torque equals to 0, V over Ke. So that is when you want to find the maximum RPM, max RPM. Okay, so when angular velocity equal to 0, dapatlah. And when angular velocity equal to 0, nanti korang masukkan. So dapatlah dia punya torque stall dia. Macam tu lah. Assume that the motor behaves ideally lah. Okay, so we also know that torque times angular velocity is the power. So power is macam tadi, just darab dengan torque. So ni torque minus torque kuasa 2. Okay, so why do we want to do this? Because we want to find the what is the most optimum power. Because usually it's like in the middle there. Usually if you have so much torque, it would usually if you have so much torque, the mechanical power akan banyak, tapi dia akan less efficient sebab angular velocity kurang. Macam tu. So so kan cakap tadi, kalau torque tinggi, angular velocity turun. Kalau torque turun, angular velocity tinggi. So which one is the best operating point? So that is where this equation comes in. So they want to do the differentiate P over torque. So equals to 0. This is like the maximum, the most optimum. Optimization. Kalau dalam maths tu panggil optimization. So you dapat ni. Torque optimum equals to V times Kt over 2R. Okay. So that soalan maybe akan tanya lah, macam mana ada satu soalan tu tadi sini. Okay, tak apa. Okay, so now we talk about the different types of DC motors. So DC motor, this is one of the components here. This is a stator, the circular housing stator. This is an armature, the internal housing. It's like the external housing, this is the internal housing. Okay, so this is like a complete diagram of what is happening inside a motor. But don't be jangan takut sangat. Benda ni semua tak penting pun, general knowledge. Yang penting tiga ni. Commutator tu is the switch of the current from one coil to another. So this is a commutator. So this when electricity lalu, dia akan power this coil, and then it will generate electricity, and then it will pusing. Macam tu lah. Stator is to produce a magnetic field. So there are two types of stator, a permanent magnet and an electromagnet. So for a permanent magnet, it's not usually called a stator lah. It's just usually called magnets, because they are basically just using magnets. But if you are using electromagnets, this is what we call a stator. Macam ni. Ni nama dia. This is a stator. Okay, so a rotor is a ring-shaped laminated iron core with slots to accommodate the armature windings. This is the rotor. Ni. This is the one attached to the shaft that will be moving around. Okay, so there are permanent magnets, self-excited magnets, shunt and series, and a separately excited magnet. Separately excited motor. My bad. Self-excited motor, separately excited motor, and there is also compound motor where you like gabung shunt and series, but I don't think that masuk because that's too much. Ni pun dah cukup susah, so kita tengok je dulu. Okay, so what is the difference between a permanent magnet motor, self-excited motor, and separately excited motor? Okay, so for a permanent magnet motor, the KT and KE remains constant at all RPM because the magnetic flux does not change. Okay, so that is what permanent magnet is lah. This is like a representation of a permanent magnet motor. This is the magnets on both ends, and the flux between the magnets will be constant from each other. Okay, so self-excited motor is a magnetic field that is generated by windings. So over here we have two different, let me put this closer to each other. Okay, self-excited motors have two windings, whereas a permanent magnet only have one winding, which is the armature itself lah. The armature or the rotor, tak kisah, sama je. The rotor itself. But this one have two windings. So usually how you want to generate electromagnetic is by using a power source kan. So this power source shares with the same power source as the armature. To the rotor, whereas the series, the stator is Okay. Sorry. Sorry, I was disconnected. Is everything okay? Okay ke? Sekarang okay. Guys, sekarang okay ke? Hello, dengar tak? Okay, dah okay. Okay. So, what is the use of the stator? The use of this, what is the difference? Okay. So, let's talk about the difference. So, for what is the excited core? What is this excited part called? Okay, so let's see. When motor is introduced with load, the angular velocity will decrease. Okay, so when the angular velocity decrease, the power will also decrease lah. When the power decrease, power equals to IV. So the IV in the over here in this section here, it will decrease. It will decrease. Since this is a constant, we assume this power source is constant. The losses is apa? The I here dah berkurang macam ni cakap. Okay, there are two I's. Okay. There are two IA and IF and IA. When the IA as in the armature, and the IA here berkurang, the IF meningkat. So when the IF meningkat, the stator will generate more electricity, more magneticity, more magnet. So it will pull the motor so that it will move again. Macam tu. Okay, wait, let me draw. Okay. So usually the graph kind of looks like this. Okay, so this is uninterrupted. This is when load is introduced. This one here happens when the IF increase. The IF is the shunt. The shunt coiling. It will attract. It will make the over here. It will make the motor move again. Macam tu lah. Okay, you guys understand tak? Okay, sekejap. When the power in the motor decrease, the power in the windings of the magnetic increases. So it will pull the motor again and it will spin again until it reaches equilibrium. So that's why the graph looks like this. This is torque over angular velocity, like that. And then when torque increase, the angular velocity will decrease and then it will increase back. This is when the shunt current increases. Naik. So more magnetic flux. Okay, let's write it. More magnetic flux by the stator, which will make the motor like stronger ataupun make the motor move again. Okay, and then when the motor move again, the torque will increase. Okay, like that. But there is a slight difference between RPM. The slight difference between RPM because the torque is needed to the torque is needed to hold the heavy load. Macam tu. Okay, so that is the function of a shunt. That is the function of a self-excited or a separately excited motor. Okay, so if you are using a permanent magnet, you don't need to worry about the flux density between the magnets because it doesn't change. But for a excited motor, the flux density in the motor will change according to the load. Macam tu. Okay. Okay, semua faham tak? Faham tak function shunt ni? That is the difference lah between a shunt and a permanent magnet. And separately excited ni lebih kurang lah, tapi dia guna different power source. Okay. So if you guys are okay, we proceed with the calculation ataupun dia punya equation lah. Okay, so for shunt series, macam I cakap tadi, dia parallel. So we use KCL. So there are two branches. One is the field magnetic by the stator, and one is the motor itself. So usually orang akan cakap RF ni field, magnetic field. Field windings orang kata, field windings ataupun stator windings. There's a lot of names lah, tapi just you need to know the concept. Just know the concept and then you will understand the different words, but it has the same meaning lah. Armature tu motor, field tu is the stator. So I equals to IF plus IA. IF plus IA. Where is IA? So I source is equals to, using Ohm's law, V over R minus V over R. The V is the V source because it is a parallel. When it is a parallel circuit, the V is the same. Okay. So when we know the V is the same, we know that V source equals to IF times RF equals to IA times RA. Macam tu. So this is the parameters that you will usually be given. As you can see here, I have numbered 1 and 2. 1 and 2. 1 and 2. What is this 1 and 2? 1 is usually the parameters that they will give. 2 is usually the parameters we want to find. Macam tu lah. Ataupun vice versa. They are all in the same category. Like, is it given or not? This requires much more calculation. This is just like this is what we call independent variables. Macam fluid mechanic dah. Sekejap. Okay. This is usually independent variables. This is the dependent variables. Remember the difference between dependent variable and dependent variable? Independent variable is usually what we control. The dependent variable is usually what we want to find. Macam tu. Faham tak? Okay. So I hope you guys wrote that down. Okay. So now we go to series. Okay. So series ni, the KE depends on the RPM because the phi changes with field current. Okay. So kan I cakap tadi, function shunt tu is to power back the motor, so to let it spin. But what happens if they share the same branch? This one, they have the V is constant, so you don't need to worry about this one and this one. So this one, when the V is constant, they share the same I. Okay. So over here, V constant, which means V equals to V. Kat sini, V equals to V plus V plus V. So there are multiple, orang kata, voltage drops. When one decreases, one increases. This one, I is this I. When one I increases, the another I increases. Okay. Okay. The shunt one, the I is constant. So when one I decreases, another increases. But for series, the V when one, usually there's only two lah. Wait. When one V decreases, one V increases. Macam tu. So it makes the calculation much more complex. Okay. So this one, I don't think dia akan masuk, tapi tak tahulah doktor nak tanya apa kan. So this is also in the syllabus, so don't worry. So the magnetic field changes proportionally with I. So we can make a relationship phi equals to KF times I. Okay, so this is the just now. The EMF equals to V minus IR, but this time it has the RF. This is the RA. This is the RF. Kat sini tak kisah, dia asing. So dia asing, tak kisah. Tapi dia sekali kat sini. So that is what makes the difference between a series self-excited motor and also a shunt self-excited motor. Okay. So we need to use all the constant we have. So we have the torque constant, we have the E constant. Okay. If you can see here, as you can see here, mana? The flux density changes. So when flux density changes, you can no longer use this. Okay, let's put here. Okay, when the flux density constant, you use E K omega, but when it changes, you use K prime omega, K prime phi omega. Okay. Okay. So torque constant times phi times I, E constant, apa? EMF constant times phi times omega. Okay. So you will find two different there will become two outcomes lah, whether you are interested into the current or in the torque. Okay, so the E here equals to susun E equals to KE prime phi omega. KE prime phi omega, phi is equals to KFI. So kenapa ada banyak-banyak macam, kenapa ada banyak ganti sebab electrical ni dia memang banyak memang banyak equation macam ni. Tak tahulah apa masalah dia tu, susah sangat subjek ni. So korang kena step by step. So ni KE prime phi is KFI. Sini. Okay. Ni daripada situ, daripada 1. This is from 1. Okay. I hope you guys can see it. So this one is from 2. So this one, let's use blue. This one is from number 2. Okay. And then what you do is you make the left hand side omega saja, and then you will find all of this. You will bahagi all of this lah, and you can see here all of these are all constants or are all independent variables. R dah bagi, R semua dah bagi. Kau nak cari relationship between the omega and the currents. Okay. But over here, different approach. Tadi kita guna ini. Now kita guna yang torque constant. Torque constant equals to KF I squared. KT prime KF I squared. Kenapa kita buat macam tu? Sebab yang ni comes from 1. Yang ni comes from 3. Three nama dia. 3. Okay. And then pindah punca kuasa, masukkan balik daripada sini. Kan sini ada I kan, masukkan balik sini. So dapatlah equation ni. Both are inverse equations. So okay, dia panjang sikit. Oh, memang panjang betul DC motor ni. Okay, so observation. As you can see here, dia tak bersentuh tau. So what does that mean? It means that it is only suitable for low RPM and high torque, because the series is very powerful. If you don't have if you tak letak load like over here, kan kat sini no load, ada lagi dia punya torque dia kan, it coincides lah. But over here, dia kalau tak ada load, dia punya angular velocity dia akan macam meningkat lah, infinity macam tu. So it's dangerous lah. So this is the usage for practical case for self-excited series DC motor. This is the importance of a series DC motor for low RPM, high torque. But for permanent magnets, you can use it for high RPM, low torque. That is the essential difference between the practical case of the permanent magnets and the series magnet. The series DC, the series DC motor. Ni permanent magnet DC motor, high RPM, low torque. Sini low RPM, high torque. So if they ask you a question, if you have macam dia tanya you, if you need higher torque, which motor do you suggest to use? So I suggest you use a series DC motor. If you have a low load but you need high RPM, you use permanent magnets. Macam tu. Faham tak? Okay, faham. Kalau faham, bagi tahu faham. Kalau nak aku ulang, aku boleh ulang balik. Okay. You guys faham tak the difference between each DC motors now? Faham? Hello guys, ada tak? Are you guys there? Hello, are you there? Okay. Sorry doh, aku rasa internet aku lag doh, aku tak dapat respon. Tapi okay. Ulang yang part pilih mana motor tu. Oh, okay. Okay. So tak apalah. Yeah. Okay, so like I said, okay, kita buat difference here. Series DC motor versus let's say a permanent. Why is it so small? Okay, sekejap tak zoom. Versus a series self-excited DC motor. Okay. Okay, so what's the difference? So this one has used for high torque, but low RPM. RPM tu dia punya omega lah, dia punya angular velocity. Kalau ni dia used for low torque but high RPM. And this will say omega. Satu, sebab the terminal characteristics there. Characteristics. Okay, you guys can write this down. Characteristics. Okay. Okay, let's make this purple. Let's make this red. Okay, so terminal characteristic dia, kalau yang series ni dia macam ni, kalau yang permanent DC motor ni dia macam ni. So dia linear, dia orang kata apa, macam predictable. Lepas tu can operate when torque is 0. But usually permanent DC ni dia punya Tmax is low. Okay, so for series ni dia inverse function lah. Dia bengkok. Dia bengkok. Yang ni dia straight, ni bengkok. So ni only operates. Hai. Kenapa? Exam. Blah blah. Only operates at a rated. Only operates at a rated torque, and ni cannot operate when torque equal to 0. This will lead to the motor destroying itself. Because that dia tak coincide dekat when torque equal to 0 ni. So dia punya RPM dia sangat tinggi. Dia punya RPM dia too high. That's why it will self-destroy. Lepas tu usually yang series ni dia punya Tmax ni is higher. So okay, macam tu lah beza dia. Okay, faham tak beza DC motor semua? This is like the special thing about series DC motor. Macam tu lah. Okay, semua faham ke? Ahmad Irfan Firdaus Pidot. Okay, kalau faham bagi tahu faham. Korang kena lukis ni. Tapi kan exam keluar satu soalan je, tahulah korang tak payah risau sangat kot. Tahu-tahu je, tak payah fokus sangat pun. Ada banyak lagi soalan yang korang kena risau. Ada DC circuit, ada magnetic circuit, ada AC circuit. Motor ni last je. So itulah, itu pun susah sikit. Tapi tak apa, kita buat je, kita belajar. Okay, alright. So lastly is the separately excited. Separately excited ni dia sikit sebab dia actually quite easy. Dia punya field current supplied from a separate constant power voltage is constant. Dia sama je. Dia tak is independent of the voltage of the back EMF. Dia tak ada back EMF ni. Dia tak ada back EMF pula. Dia tak ada motor. Jadi separately excited uses a different power source. Okay, so usually untuk separately excited motor ni, use case dia is bandingkan one situation and another situation. Dia macam before and after. Before ni berapa RPM, after ni berapa RPM. Macam tu. Because dia punya KE dia is sama. KE equals to KE because we assume this to be constant. Faham tak? So ni KE dia sama. Sebab kita assume ni constant. So I dia constant, R pun constant. So dia punya power pun constant lah. Dia punya TW. Tapi masalahnya dia tak berpusing. So dia punya IV dia, IV dia constant. So what it has is just the KE. Okay, so that is the separately excited motor. So this is all the question, the macam ni semua macam example, example for each different motors. Okay, now kita masuk example. Okay, so example ni aku ambil dari internet sebab aku tak sanggup nak salin balik. Okay, so we have a shunt motor draw 6 kilowatts from a 240 voltage line. Okay, jap. Sebelum kita masuk ni, kita rehat 5 minit. Rehat. Take 5. Banyak sangat nak absorb ni. Okay. Take 5. Sekejap aku nak buang air. Take 5. Okay. I'll be back. So we're back. Okay, kalau ada soalan boleh tanya. Tak ada, kita proceed soalan. Hello, I am back. You guys have any question? Can write. Tadi ada silap sikit. Ini bukan T, bukan talk, ni time. Overtime. Ini angular velocity. Okay, so kalau tak ada, kita teruskan Oh, satu nak tambah. Ini series kan. Kalau shunt, self excited DC motor. . . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay, so kalau shunt ni dia sama, dia behave like a permanent DC motor. Sebab the only thing beza dengan DC motor, dia ada shunt ataupun field windings in the stator changes phi only when load is suddenly introduced, and then it will return constant after a while. Macam tu. Kan tadi kita ada cakap yang this is time, this is uninterrupted, this is load, this is dia equal balik. Macam ni cakap, balance. Dia balance. Balance balik. Okay, balance balik. So itu dia punya shunt punya properties dia. Dia sama je macam DC motor tu, dia linear juga. Okay, so kalau tak ada, kita proceed dengan example. So this one. Okay, welcome back to the live stream. So now we want to do first example. The shunt motor draws 6 kilowatts from 240 volt line. If the field resistance is 96 ohm, determine the line and the armature current of the motor. So yang ni, this is the armature current IA, this is the shunt ISH, this is the resistance. So dia suruh determine the armature current, suruh cari IA. So usually kita use KCL tu lah. Ni KCL. This is the KCL. Okay, this is the KCL, and then just ubah je sebab kita dah tahu IL. Kita dah tahu shunt motor draw 6 kilowatt. So 6 kilowatt is the power, total power. Shunt motor ni is the include motor plus motor and shunt. Okay, so it's 6 kilowatts. So 6 kilowatt is the power. P equals to IV. VI. So dia cari I. I ni berapa? 25 ampere. So use KCL. I in equals to I out, and then you will find this. So 25 equals to berapa ni? ISH plus IE. So kita cari ISH. ISH ni is the V. V over R. So macam aku cakap tadi, V source sama. So IR. So ni A, ni RA. V source sama juga dengan ISH darab RSH. So kita cari ISH. Kita dah tahu RSH, kita dah tahu V source. So ISH equals to V source over RSH. So tu yang dia buat ni. So dapatlah 2.5. Tolak dapat I armature equals to 2.5 ampere. Okay, that's the first example. Second example, dia suruh cari it's the same lah. My bad. What the heck? This is not the same. Loss, okay. Example 7. This is shunt connected DC motor. Shunt connected DC motor. This is a separately excited DC motor. This is a series connected DC motor. And this is a series DC motor. Permanent magnet lebih kurang sama je. Nanti kita tengok balik. Okay, now kita tengok shunt. Shunt. Okay, so shunt 230 volt motor operates at 1200 rpm. The rotor current is 200 ampere and the rotor coil resistance is 0.2. Rotational loss due to friction is 500 watts. What is the load torque? Okay. So kita write down dulu. 230 volts, 200 ampere, omega equals to 120 rpm. Friction loss is 500 watts. So dia dah bagi sini rotor current. Okay. Rotor current, which means the IA or the I motor. Dia ada banyak nama. So you guys just hafal the principle. This is the rotor. So dia dah bagi 200A. So senang lah. Senang. So okay. EMF equals to 230 minus IR. IR ni apa? IR ni is the IR equals to 200 times 0.2. Dapat apa? 40 volt. So 230 minus 40 dapatlah 190 volt. So the electrical power developed is the I times ni. So dapatlah 200 times 190, 38 kilowatt. Mechanical power is the macam kita cakap tadi tu, over here. Ni kalau ada due to friction ke apa, EI minus tu, so akan dapat tu. Okay. The mechanical power. Okay. EI minus EI tadi minus loss. EI kita dapat 38 minus lah dengan loss tu 500, dapatlah 37 500 watt, 37.5 kilowatt. Okay, so 37.5 kilowatt sama dengan torque omega. Kita tahu omega, so bahagikan. 37500 over berapa omega dia? 1, 2 darabkan dengan 2 pi over 60. 60 to 100 sama dengan 20 to 40 pi. Okay. So kalau tekan calculator 37500 bagi 40 pi, dapatlah 298. 298.416 Newton meter. Sebab dia suruh cari torque. Okay, senang je. Exam nanti korang just ambil tahu je. Sebab banyak sangat benda kalau nak masuk. Dia satu soalan je. Ada lagi banyak soalan korang kena risau. So korang tengok-tengok je. Tak risau sangat lah. Senang je. Senang je. Ni separately excited DC motor. So when it is separately excited, the KE it will say that with a constant field current, drawing an armature current of 500 ampere from a 120 V source. Okay, so this is V source. This is the this is not accurate lah, tapi biar je lah. Korang lukis je macam ni. Separately excited DC motor. Okay, the armature resistance is 0.1. If the mechanical load changes such that it now draws 95 ampere, determine the speed of the new load. Okay, so this is the use case of a separately excited DC motor. So at 145 rpm, dia ada 50 ampere, dia ada 120 volt, dia ada 0.1. So kita boleh tahu dia punya EMF dia berapa. 120 minus 50 times 0.1, 115 volt. So dia punya constant EMF constant dia equals to E over W over omega. So you will get this. Okay, you will get, okay, let's put in our calculator, equals to 115 bagi malas tu nak tukar RPM. Tak payah tukar RPM. Don't need to tukar RPM sebab kat sini dia nak RPM juga. Okay, so 115 bagi dengan 1045 dapat 0.1100. Okay, so at unknown speed, tak tahu berapa, dia punya stay the same, R stay the same, tapi it changes the current. It changes the current. Okay, when it changes the current, it will change the EMF. So it will get 110.5 volts. So bahagikan ni, dia nak cari omega. Kita tahu KE dia berapa tadi, 0.11. So W equals to W equals to 1105 times 0.1. Bahagilah. Maaf. Dapatlah 1 ni RPM. Okay. Kalau dia gerak-gerak, kenapa lah dia nak gerak-gerak ni? Okay. Now series example. Okay, stator, rotor. So 220 volt, 0.5 resistance, stator winding, resistance of 1.5. So ada stator, ada rotor. 220 stator, rotor, and then this is the motor. Okay, so okay, kan circuit diagram ni kan ada benda bulat ni. Benda bulat ni tak letak pun tak apa, sebab benda bulat ni dia bukan tak penting, cuma it is not a component that has a value, because we represent the values in the resistance. So it will just look like a normal circuit. It will just look like this. You don't need to put yang bulat-bulat ni. It only represent the armature, the stator. It only represent the stator, doesn't represent any value. The only one representing value is the resistance here. Okay, so you guys, kalau keluar circuit pelik tu, korang tahulah mana satu represent mana satu. Okay, so this is the stator, this is the rotor. So this is the internal motor, draws 20 ampere at 1200 rpm. Perasan tak, dia punya ampere je yang berubah, dia punya voltage dia tak berubah. Sebab DC motor kita assume voltage is constant. So power is a function of I itself only, because this V is a constant. So the power is only a function of I, which is VI. Okay, I hope you guys understand. If both of these are variable, it will make it more harder lah. Variables tak boleh. Satu je variable, which is I. This is constant, because the P is different according to the load given. So if heavier load, the power will increase, ataupun the required power increase with heavier load. Okay, that is why usually V is constant and the current is the one that changes. Okay, so the rotational loss is 150 watts. Find the output power and efficiency. So this is the EMF, 220 minus, this is the what this is the sepatutnya kan series kita letak atas tu, E equals to V minus I R field plus RA kan. So let's just do it lah. 220 minus I dia berapa? I dia 20 darabkan dengan 1.5 plus 0.5. Betul. 1.5 0.5 dapat 2 40 180 volts back EMF dia. Alright, so darab nak cari electrical power dia, darab dapat 3.6 kilowatts. So the mechanical power is including the friction, which is 150. You will get this. So output power bagikan dengan VI, dapatlah 78%. So that is the output power and the efficiency. Okay, so this is the last one, which is the series DC motor again, but if different use case, which is a fan. Okay, kita tengok sini. The torque is proportional to the square of the speed. Okay, why do they say the torque is proportional to the square? Is proportional to the square sebab if you can see here, kat sini, this is where it proves that the torque is proportional to the current squared. Okay, so okay, that is one proof of our equation. Proportion square of the speed. Oh, maaf, speed bukan current. Speed. So not this one. Torque is proportional to the square of the current. Over here lah lebih kurang. Kan ni kan punca kuasa 2, something like that. Wait. So torque punca kuasa 2. Kuasa 2. Okay. That is this. Okay, and then the armature core resistance is 0.6. The stator winding resistance is 0.4. Okay, so we know our RA and the stator winding. Tak kisahlah korang nak panggil apa, RF boleh, R stator boleh. The motor draws 25 ampere when driving the fan at 300 rpm. As you can see here, even driving the fan is low RPM, 300 RPM. So it means that it is introducing a lot of torque. Okay. Determine the power supplied to the fan and torque developed. Okay, so at 300 RPM, we have our equation here. V minus I, R plus R. This is V, this is I, This is R, this is RF, this is RA. Okay, darab I ni is 25. You will get 195 volts. So power output, since dia tak mention pasal mechanic frictional loss, assume no friction. Okay, so EI equals to T ni. So carilah torque. So torque dia dapatlah 155.25. Okay, 155.45. So darab lah dengan P output dia. So we assume it to be 100%. 100% ke? No. EI equals to 195 sini. 25 is the 2. Okay, so let's dia tak minta efficiency ke, kita cari je efficiency. Equals to TW over VI. So TW kita dapat ni tadi, T15. Kalau tak pun tulis je balik EI over V dot I, sebab dia sama kan, dia sama. So tulis balik 195 times 25 over dia punya V dia berapa? V dia 220 times 25, cancel out, dapat lah 195 bagi 220 darab 100, 88.6%. Okay lah, okay, faham. So that is the efficiency of the fan lah. Okay, so next dia minta when the motor is connected to the same source with an external resistor in series, the speed is reduced to 200 rpm. We determine the value of the resistor and the power supplied to the fan. So dia bagi R kat sini. So we need to make one equation here, which is the EMF. This is our V, this is our I, this is our R1 plus R2 plus R3. Okay, so both of these are unknown. We don't know I2 because I is wait, let me put that, because torque is KTI. Kita nak cari KT, but this is a series fan, so KT dia kena guna phi. So kita tak tahu ni, kita nak cari tu tapi kita tak tahu. So okay, let's go one by one. So this is the first equation. So this is the second equation, E2 I2. Kita darab daripada EMF ni 1445. How do we know this answer? Oh, this is where do we find this? Okay, dia tak cakap lagi. Oh, maybe aku skip steps. Sorry. So this one later, not yet. Ni KE equals to KE. Remember I said about the Weber, about the phi thing tu. So kita assume yang KE ni kan equals to E over W, tapi sebabkan dia series, kita letak Weber. Okay, so Weber ni also complicated kan, electrical ni is directly proportional to I. Okay, tengok atas ni. Ambil kau. Untuk series, the phi changes with field current with I. Okay, so this is the full equation, full derivation. But sini dia cut corners lah. This is one way to cut corners. Kena pandai lah, dia cut corner. macam shortcut macam tu. So plug in. The only thing you don't know is what did I do? Jap. Back. Okay. So the only thing we don't know is the back EMF and the I. We know the first EMF, we know the first RPM, we know the first I. So okay, you will find this. Then EI equals to berapa? TWO T omega. Okay. Dapat dah. So how we find this is actually using torque times omega. Torque is 69, omega is 2.94. From here, torque dapat mana? Torque dapat mana? 69. Where did you find this torque? Sekejap, tengah fikir macam mana dapat 69 ni. Stated. Dapat 69 ni. Tak apa. Jom. P output sama dengan tu. Do we have other equations for torque? Ni lah kan, P ni dengan mechanical power ni. Okay, weird, I don't know. Cap. Have I missed anything? Korang tahu tak mana dia dapat 69 ni? Cakap. Oh, I know. EI equals to torque W. Betul. Okay. So E tak tahu, I tak tahu, T here, W here. Where did you find torque? Tak tahu tu. Okay, kena tengok video tu balik. Okay, sekejap. Hold on a minute. Okay, pause. Let me cari sekejap.
Pass IT certification exams with exam topics, offering real exam questions and answers.
And speed is 300 RPM. 802. Voltage, we know the. I can now find my output power since I know both the torque and the speed. 1,400 and the current, and we know the mechanical speed. So we have enough information to find the torque. The torque here is 155.25 Newton meters. The output power is 4,875 watts. Since it's a 5.2 kilowatt motor, we can see that the motor is not 100% efficient. In this problem, the difference is due entirely to electrical resistance. Since we know the torque and we know the speed, we can now find the torque in our second situation. Our torque works out to be 69 Newton meters.
Oh, okay. Dah dapat jawapan dia. So, how we find the torque is by using this tadi. Torque is proportional to the square of the speed kan. Okay, so I terlepas pandang ni. So T is this one. So T1 equals to omega 1 squared. So T1 over omega squared 1 is equals to T2 over omega squared 2. Okay. So T1 tadi kita dapat 155.25 over berapa RPM dia? 31.42. Ni kita squared kan. Lepas tu kita tak tahu top ni kan, tapi kita tahu RPM ni. RPM ni 20.94. Okay, 20.94 squared. Okay, so kita cari top ni. Top ni equals to okay, kita darab dulu. 155.25 over 31.42 darab squared darab 20.94 squared. Okay, so dapatlah 68.956. Equivalent lah dengan 69. Macam tu. Okay, so that's how they got it. Ni radians per second. Okay, we got it. Okay, now we know this. Okay, so from 1 and 3 kita boleh cari. Okay, sekejap kita padam ni, delete. Okay, so we know that EI equals to 1445. We know that 195 over 31.42 25 equals to E 20.94 I. Okay, so kita letak E as 195 times 20.94 over 31.42 times 25. E naik sekali dengan I. So kat sini korang akan dapat 195 times 20.94 over 3.1.42 times 25. 5.1983 I. Okay, so E works here. So letakkan dalam ni, so akan dapat 5.1983 I squared equals to 1445. I equals to, cuba cari I equals to berapa. 144 macam kuasa 1445 over 5.1983 16.67. Kejap. I equals to 1445 over 5.1983. Okay, kau akan dapat 1667. Okay, dapat. Okay, so that is I. So from there we can find E. Okay, E equals to 1445 over, using this equation here, over 16.67. E akan dapat 1445 bagi answer 86.669. Dapat E. So dah tinggal R je. R masukkan dalam equation ni. Okay, sekejap kita buat sama-sama je guys. 86.669 equals to V is 220 minus I is 16.67, R plus 04 plus R plus 1. So R is equals to ni bawa pergi sana. R plus 1 equals to 220 minus 86.669 over R1 16.67. R equals to 220 minus 86.669 over 16.67. Oh, dapat 8, which is 7.998 lah, minus 1 dapatlah 6 R equals to, oh no, R equals to 7, R equals to 6.9998, which is equals to 7 ohms. Okay, dapat dah. Okay guys, so that is all for DC motors. Berapa jam kita ni? Berapa jam dah? Sejam 47. Okay, so we spent 1 hour on explaining and 47 minutes on doing examples. Okay, so ada semua okay? Semua faham tak? Boleh study topik lain dah lepas ni, tak risau DC motors. Okay, so if you guys have any question, please ask. Don't need to rush and don't need to worry too much. This is just 25% of one paper. I don't think doctor will ask that much lah. Paling-paling pun tanya soalan senang lah. Kita just ready je lah. Okay, so I think that's all from me. Thank you for watching. Thank you for staying until the end. Sekarang ada 9 viewers. Thank you all 9 viewers for watching my stream. Thank you very much. Okay, bye bye guys. Thank you.